right. All right. This is 07. All right. Welcome back, everybody. If you have any questions, please ask before we get started.
About the previous the homework assignment, sir?
Yeah, for sure.
Okay. Let me see if I can find it. 1.4, number 7.
1.4, number 7. Let me get there. Let's see. John 1.4, number 7. Is the x to the 6th? That one?
Yes, that is
Okay.
correct. Yes.
Okay. Cool. Did I put that in 1.4? Help, I sure did. Oh, well. All right. Let's see. 1.4, number 7, and x to the 6 plus 63x cubed minus 64 equal to 0. Okay, so I'm assuming you went U substitution.
Yes, sir. Using the U method, I believe.
So U equals x cubed, and therefore U squared should be x to the 6, right?
Yes.
Okay. So put that together, and you'd have U squared plus 63 U minus 64 equal to 0. And that should factor to U plus 64 U minus 1. U squared negative U 63, 64. And U would equal negative 64, and U would equal 1. Okay. And then bring back U. X cubed equals negative 64. X cubed equals 1. Okay. And then you would cube root both sides. And over here, the cube root of negative 64 should be negative 4. And the cube root of 1 is 1. So where were you having issues with that one?
Definitely right at the beginning where he actually cubed the x to the third equals negative 64. That's where I was originally stuck at.
Like right here, right?
Yes.
Yeah. Okay. So yeah, so in order to get, of course, to get rid of it, you would cube root both sides, but I guess you have to have a little understanding of cube roots. So remember, you can cube root or odd root anything, positive, negative, and you could even do the odd root of 0.
Oh, of course, because I referred to my previous notes in the Math 0320, and for some reason, I had 4 answers because I had to use the quadratic formula for that.
Oh, I guess that's what you're saying
Yes.
is why don't we have 6 answers, right?
Yeah, pretty much.
Okay, well, basically, since that is to the power of 3, that means that this negative 4 shows up 3 times.
Mm-hmm.
And this 1 will show up 3 times. So we'll learn more about it once we start getting into, I think, chapter 5.
Okay.
It's called the characteristics of polynomials. And we'll learn about something called multiplicities.
Okay, understood.
Yeah. So this would be considered to have an odd multiplicity of 3 because negative, well, both of them would have an odd multiplicity of 3 because they both show up 3 times. And
Understood. That
that's
actually
it.
clears up. Thank you, sir.
Okay, cool. All right. What else, kids? Any other questions before we get started?
So, is there maybe like a faster way when you get like the solutions to like kind of automatically see if it's not going to work out or not?
Like if it's not factorable or anything like
Um,
that?
when you get like the solutions of like x, for example, here like x equals -4 or x equals 1, is there like kind of like a quick way to see if maybe one of them doesn't work?
Oh, like when plugging them in?
Yeah.
Uh, calculator.
Okay.
Yeah. So yeah, I mean you'll plug them in, but yeah, I mean I don't want to know what 4 to the 6 is, so I'd use a calculator for that.
Okay.
Carl probably wants to know what 4 to the 6 is, but I don't.
Why am I being attacked right now?
Nothing.
What did I do to deserve this?
Casey's asking for the problem number 14 on 1.4 to be done on the chat.
Oh, okay. Let me go look. Questions. Cassie, number 14 on 1.4. Okay. Cassie, there we go. Number 14. Ooh la la. Ah, okay. Cool. All right, good times. Man, I know there's cedar in the air, but today I'm just really messed up by allergies.
Yeah, I'm dying too. It's getting my dry eye syndrome.
Yeah, because I've been loading up on everything for the past couple of weeks, but today is just like, bam. But I did go out to Blanco this weekend where there's tons of cedars, so I'm dead.
It's pretty rough.
All right. So they give us k equals x plus 1 over x minus 1, and they give us k squared minus 3k equal to 10, and they say find x. So basically what happened here is they already did the u substitution for you, but they used the k instead. This is k substitution. So they replaced all the terms with k. So all we have to do is solve for k and then bring in what the substitution for k is. So the first thing we're going to do is move over that 10 and factor. And this should factor to k minus 5, k plus 2 equal to 0, k squared 2 minus 5. Good. And you'll get k equals 5 and k equals -2. But now we know that k is x plus 1 over x minus 1. So we're going to bring that in. X plus 1 over x minus 1, equal to 5. And x plus 1 over x minus 1 equal to -2. And let's just go ahead and solve for x. So what we're going to do is just take this denominator and multiply it to the right side on both of these equations. And I'll get x plus 1 equals to 5 times x minus 1. X plus 1 equal to -2 times x minus 1. And then just solve for x. So x plus 1 equals 5x minus 5. X plus 1 equals -2x plus 2. Move my x over. -4x. Move my 1 over. -6. And then move that x over. -3x equals 1. And then we'll get divide by -4. And x is going to be 3 halves. And then divide by -3. And x is going to be -1/3. Or should they both be positive? Did I mess up a sign somewhere? Negative 2x plus, oh yeah, when I add that 2 over, it's positive. So yeah, watch your signs. There you go. Cool. All right. Again, if you got a question, ask away. Other than that, I'm going to post the notes that we're covering in the chat. 14. I think we have 3.1 today. Yes. So there you go. There's 3.1 notes in the chat. And then Ethan, 16 on 1.4. Oop, where'd it go? 16 on 1.4. Oh man, it's just like 15 or 14. So for 1.4, number 16, it's 1 over x plus 3 squared equal to 1 over x plus 3 plus 20. I'm going to move everything over to the left side. So you'll have 1 over x plus 3 squared minus 1 over x plus 3 minus 20 equal to 0. And then all we're going to do here is u substitution. So u is going to cover this whole fraction, which means u squared will cover that one, which means we get u squared minus u minus 20 equal to 0. Factor u minus 5, u plus 4 equal to 0. 4 minus 5, good. Then u would be 5, u would be negative 4, and all we have to do is bring back what u was. Oops. Okay. And u was 1 over x plus 3, so this becomes 1 over x plus 3 equal to 5, and 1 over x plus 3 equal to negative 4. Multiply the x plus 3 to the right side, and 1 would equal 5 times x plus 3, and 1 would equal negative 4 times x plus 3, and 1 would be 5x plus 15, negative 4x minus 12. Move over that 15. What's that? Negative 14 equals 5x. And then move over that 12. 13 equals negative 4x. Divide, divide. And we get negative 14 over 5 equals x. And negative 13 over 4 equals x. So ugly. There we go. You are welcome. Oh, this pen tip gets so dirty. Maybe because I spit on the screen while I talk, and then I write over it. Okay. If no other questions, then we can get going with 3.1. New stuff, new stuff. Okay. Today is all about functions. So we're going to learn the definition of a function. I think you guys saw it in 0320, I believe. But we'll go a little bit into more detail. So a function is a relation in which each element of the domain corresponds to one and only one element of the range. So to put it simply, the first components are all unique. If you look at the pictures of my blobs, the first picture represents a function. So we see that here, the blue one is our domain. Whoops, where did I go? There we go. The blue one's my domain. So A goes to 1, B goes to 3, C goes to 3, and D goes to 4. So what we see is that every X value in my domain goes to one and only one element in the range. And it is okay if multiple X values share the same Y value. What is not okay if one X value has multiple Y values, which is in the picture to the right. So here we have A going to 1, perfect. B going to 1, that's good. Multiple X values, same Y value. Okay. But then you have C going to 2 and going to 3. So this is not a function. So this means that one X value cannot have multiple Y values. And then D goes to 4. So since one X value went to multiple Y values, that is not a function. What we're focusing on today is what is a function. So remember, every X must have one Y. And it is okay if multiple X's share the same Y value. Okay. So now, any questions on that before moving on? That I heard somebody. Okay. So now we are going to be given equations and we want to determine if these are functions or not. And one of the easiest ways to determine whether you have a function or not is based on the exponents, powers, or degrees of the given equation or function. So here we see that y is to the power of 1. It's just y by itself. Here we see that x is to the power of 1. So once again, one of the easiest ways to see is if you look at the degrees, the exponents of an equation given. Since x and y are both to the power of 1, this means if I plug in an x, I get a y. So if I plug in 1x, I'm going to get 1y. And if the powers don't do the trick for you, well, another way to do it is, hey, make an XY chart. Let's go ahead and pick points and see what happens. So if I just made a quick XY chart, and let's just say I picked -2, -1, 0, 1, 2. Just pick some common points here. I take all these X values and I plug them in for X into this function. So that would give me -4 minus 5, -9, -7, -5, -3, and -1. So what we see now, based on my XY chart that I have drawn or created, is that every X value has its own y value. You do not see an x value that has two y values. So this can also determine that this is a function. All right. And then another way to determine that you have a function is, well, graph it. Y equals 2x minus 5 is a linear equation, which means that's going to be the graph of a, it's in the name. Linear means anybody?
Straight line.
A line, right? So my graph would look something like this. Just a sketch, right? My graph would look something like this. And another way to prove that this is a function is that if I show an x value here, let's say I have an x value there, and I go up, I get an exact y value there. Nothing repeated. So once again, for one x value, I get one y value anywhere on this graph, no matter where. I could pick a point down here. I would have an x value and one y value. So again, to be a function, every x must have one y value. They cannot have multiple values. I guess I could put the powers thing over here. Let's see. Power of x is 1, and power of y is 1. That means it is a 1 for 1. Okay. Any questions on that? Okay. Number 2, determine if the equation x squared plus y squared equals 1 defines y as a function of x. Well, what do you guys think? Oh man, anybody live out there? Well, to start with, what are our powers?
They're both 2.
They're both 2. So maybe that's not a good enough giveaway for us, right? But this means that it could possibly mean that if I plug in an x value, I'll get 2 y values, right? But if that's not good enough to prove that this is a function or not, well, let's go ahead and solve this equation for y. So I'll rewrite it here. X squared plus y squared equal to 1. Then we go ahead and solve for y. So I'll move the x squared over, and I get 1 minus x squared. Then, in order to solve for y, I'll square root both sides. And I'll get y equals plus or minus the square root of 1 minus x squared. Which maybe now you can see it, because now if I plug in an x value, how many y values am I going to get?
2.
2, which means, is this a function or not a function?
Not a function.
Not a function. Good. Oh, up here should have been function. So this is not a function. So maybe our dead giveaway here is if y is squared, then we're not going to have a function. Okay. And again, another way to prove it, let's just go ahead and make a small XY chart. And this time, I think I'll just choose -1, 0, and 1. And if I plug these numbers into this function, I'll get 1 minus, what is that, -1 squared? Oh, that'll give me 0. We can't have plus or minus 0. But then, if I plug in 0, I'll get the square root of 1, which is going to give me plus or minus 1. And then I'll get 0 again if I plug in 1. So what tells us that this is not a function is that this x value of 0 has how many y values? Again, 2. Good. All right. All right. And then last, again, just to double check, we can graph this function. Does anybody know what type of graph that this equation makes? And it's okay if you don't. Maybe you've never seen it before. But this equation is the equation of a circle with a radius of 1. So if I were to plot an x anywhere on this circle, if I go up, I get a y. If I go down, I get a y. Again, showing us that this one x value has two y values, and therefore this is not a function. All right, not bad. Okay. So powers, XY chart, graph it, whatever you have to do to determine whether it's a function or not. Okay. 3. All right. Y equals 3x minus 1 over x plus 2. What do you guys think? Function or not a function?
Function?
Function. Good. Why do you think so?
I don't know, because it's not squared. I just guessed.
That's a good enough reason. Y is to the power of 1 and x is to the power of 1 in the numerator and denominator, right? So this again is one of the easiest giveaways. If I were to plug in an x value, I would only get one y value as the output. So powers can give it away. So again, this would be a function. And you guys most likely don't know how to graph these yet, but we will later in the semester. And a graph like this would look, let's see, it would look something like this. I would have that, and then I would have 1 at 3. So you would have something that looks somewhat like this. Where again, if I were to plot an x, I'd have one y value. If I were to have an x, I'd have one y value, no matter where on the graph. Okay. So those are multiple ways to determine if you have a function or not. Okay. Any questions on that page? All right. No, stop it. Okay, so move on to the next one, finding values of a function. So functions are denoted by letters such as F, capital F, G, capital G, whatever you want to name the function. Choose a letter of your choice. If F is a function, then for each number X in its domain, the corresponding image in the range is designated by the symbol f of x, read as f of x or f at x. Remember that x is the independent variable and y is the dependent variable. So y always depends on the input of x. You input an x and the output's always a y. So all we're going to do on these examples is, given this function, we're going to evaluate it given a certain operation. So for number 1, it says f of 3. This means that we want to know what is the value of this function when x is exactly 3. So with that being said, what number will you plug in for all the x's on this one?
3.
3. That's it, right? Nothing crazy on this one. You'll get 2 times 3 squared minus 3 times 3. And all we have to do now is simplify. So you'll get 2 times 9 minus 9. And you'll get 18 minus 9, which gives us 9. So what we're saying with this function notation is that when x is exactly 3, the value of y is 9. Okay. Next, this says 3 times f of x. So all we're going to do for this one is take the function and multiply it by 3. We're not substituting anything in. We are multiplying the whole function by 3. That's it. So distribute that 3, and we get 6x squared minus 9x. Okay. Next is f at negative x, or f of negative x. So once again, we're now going to take negative x and plug it in for every x into the original function. So this will look like 2 times negative x squared minus 3 times negative x. So we plug a negative x in for every x in the function. Okay. And now our end result, so negative x squared means negative x times negative x, of course, becoming positive. So we'll get 2x squared plus 3x. So again, negative x squared is negative x times negative x, which gives us the positive x squared. Okay. Next one. Negative f of x. So once again, just take the function and multiply by negative 1 on the outside. So you'll have the negative out front, plug in your function, 2x squared minus 3x, distribute that negative, and we're done. Negative 2x squared plus 3x. Okay. And was that it for that page? Oh, sure was. Okay. So that is just how you evaluate and simplify a function. Given an input, plug it in, put parentheses around it, simplify. Okay. Any questions on that page? Seems pretty straightforward. All right. And now, on to my favorite. All right. This next page is all about the difference quotient, okay? So this will test your algebra skills. You'll see the difference quotient a lot when you get to calculus, because all it is to us right now is just an algebraic practice. It gets us better at being better at algebra and just getting your skills on par. So what the difference quotient actually is, it is called the definition of the derivative for calculus. But that's only when you get there. What the difference quotient does is it helps you find the slope on a function at any given value of x. But again, we don't have to worry about any of that until you get to calculus. Today, you just get to simplify it. You get to, given a function, you get to apply the difference quotient function and simplify it. So I'll walk you through those steps. This involves a lot of algebra, and it's very easy to make a mistake. So just watch all your signs. Okay. So what we're going to do is call this step A. The first step we want of the difference quotient function is to find f of x plus h. So we're going to look for f of x plus h. So what this means is take x plus h and plug it in for every x into the given function and simplify. So we'll get 2 times x plus h squared minus 3 times x plus h. So we're plugging x plus h in for every x. And now we must simplify. So x plus h squared means we have 2x plus h's. So 2 times x plus h times x plus h. And we can go ahead and distribute that -3 already. And now we're going to FOIL x plus h times x plus h. So when I FOIL this, I'll get x squared plus xh plus hx plus h squared minus 3x minus 3h. All right. And then we'll combine like terms. We can add the xh and the hx together. They are the same term. They have the same variables. So let's just go ahead and clean that up. And I'll get x squared plus 2hx or xh, whichever you prefer, minus 3x minus 3h. Okay. And now I'm going to help you out and save you some time for later difference quotient problems. So this piece right here, just know that if you ever see x plus h squared, just know that automatically this will FOIL to x squared plus 2hx plus h squared. If you know that, you will save a lot of time. Because look how many steps we've done so far. We got 1, 2, 3, and now we're on 4, right? So you can shave off a step or two if you know that. Because we're not done yet. We still have to distribute that too. And then we have 2x squared plus 4hx plus 2h squared minus 3x minus 3h. And step A is done. All right. Make sure you didn't make any mistakes. Watch your signs, because now we move on to step B. And step B, I'll do a different color, wants to know the rest of the numerator. What is f of x plus h minus f of x? So I'll write that here. B, f of x plus h minus f of x. So we're going to start right where we left off. Ooh, can I cheat this a bit? Let's see. Selection tool, go. Duplicate. Do things. And then I can click here and paste. Oh, and that went somewhere else. Very nice. Okay, I went down here. Oh man, I'm already running out of room. So I'm just going to copy and paste that there and change the color to red. Look at that. Technology is great. Nope, you stay red. Okay, so we are rewriting what we finished off with in step A. And now what we're going to do is subtract the original function. We're going to subtract the original function that was given above. Oh man, I messed everything up. Right.
Sorry to interrupt you, but before you go further, I think you forgot an H on a the -3 at the
Oh,
end.
you're good. See, it didn't copy that over. I messed up a bunch of stuff. No. All right. Or maybe I never wrote it down. Good call. So you see how easy it is to mess something up? Don't do it. 2x squared, 4hx, 2h squared minus 3x minus 3h minus, okay, now we're going to subtract the original function. 2x squared minus 3x. And can anybody tell me what I forgot when I plugged in the original function?
Parentheses.
Parentheses. Good. Whenever you plug in the original function, you need parentheses. If you don't put those parentheses there, you're going to mess up everything. All right. Hang on. Give me a moment. Let me see if I can fix what I just did. Bad. How'd that? Oh. Somehow it minimized the page. That's crazy. Hey, there we go. Almost there. And voila. I'm back to normal. Okay, cool. All right. No more tricks then. All right. So what we're going to do is, unfortunately, rewrite everything and distribute that negative. And now step B is the most rewarding part because terms start to cancel. So what terms do you see that we can cancel?
The 2x squared.
2x squared is gone, and what else?
The 3x.
The 3x. So we cancel those and rewrite what we have. 4hx plus 2h squared minus 3h. So that's what's left over from step B. So this is the answer my math lab is going to take because in small blue writing it says do not factor. So this is what it wants. So I'll put this is MML. But what I like to do to finish off step 2 is I like to factor out an h. So it's just going to make the final step a lot easier. So I'm going to factor out an h, and that's going to leave me with 4x plus 2h minus 3. Okay. And I know I'm running out of room, but I can fix it when I'm ready. And that's how you end step B. You factor out the h, and now we move on to step C. And we want the whole difference quotient. F of x plus h minus f of x all over h. And we take what we ended with in step B, and I put that in the numerator. H times 4x plus 2h minus 3. I put it all over h, and what's going to cancel?
H.
H's. And we get our final answer of 4x plus 2h minus 3. Look at that. Beautiful, huh? Now you see how easy it is to make a mistake when you're going through all that work, right? So just
So you're saying in my math lab, we only need to find the numerator?
no, well, everything I've boxed is an answer so far, but I'm saying that so yeah, in my math lab, it's gonna want steps. Basically, is everything I put for A, B, and C is gonna have those input boxes for. Yeah. So this would be an answer for the first one.
Gotcha.
And then
Okay, so it's going to ask for each step.
exactly.
A, B, and
so,
C. Okay.
So everything I boxed is going to be what you're going to do in my math
But for
lab.
step B, you're saying they don't want us to factor anything out. Or...
Exactly. You're going to
Okay.
see in small blue print, it says do not factor. Just leave it as that big, ugly statement.
Oh, that jerk. Okay.
Okay. And that is the difference quotient function. So just so it's not a bunch of algebra and you're like, oh, that's a lot of work, which it is, but it's good for you guys. What this equation does, this difference quotient does, is it finds the slope at any x value for this original function. So I don't know. I think that's pretty cool, but that's when you get there. You still got to get through pre-cal. All right. Any questions on that process? Good. All right. Then number 2, I'm going to leave you on your own. Go ahead and try number 2 out. Oh boy, right? And then Carl, I'll have you work through it with them. Number 2.
You want me to do that right now?
We'll give them like a couple of minutes and then jump in.
Gotcha.
Let's see how far they get. You want me to work?
That's exactly how I intended it to sound too. What is this?
What is this when I can get the answer in less than a second, right?
I didn't stay up to do this. I don't know, man. Sometimes algebra can be fun, but the difference quotient is not one of those times.
Dude, imagine when because when I teach the difference quotient, all the other classes line up that I teach, and so I do the difference quotient for like a week straight.
Oh no.
So like business cal is going to have the difference quotient tomorrow, and then calculus is going to have the difference quotient on Wednesday, and then and then my other business calculus will have the difference quotient on Thursday or on Wednesday. I'm like, oh my goodness.
No, not to dog the business cal people, but I'm surprised you just don't show them how to use a calculator to find the derivative and skip that entirely, you know?
Everybody got to go through everything.
That's what they tell you.
Woohoo. All right.
Where's the link to your OneNote so I can do the notes there?
I'll send it again. Let me stop this. Boom. And then you're not that person and that person and this and share. Oh, share. Anyone with link can edit. Copy. Copy.
Oh, Hopper.
There we go. Bam. Oh, I sent that to everybody. Oh well.
Whoops.
Oh well.
Everybody
No.
delete your eyes.
Now feel free to go delete all my notes, okay?
All right, let's go ahead and share this screen. Very dangerous sharing a web browser page.
There you go.
All right, let's find, we're at 3.1, right?
There you go, yeah.
There we go.
2021.
All right. Okay. Let's get tortured here. Okay. So, since I learned this from Professor Carrillo,
Oh
I
yeah.
also learned how to do it his way, which is one. That's a little thin. I don't like how thin that is. Do it just a little bit thicker. Yeah.
There you go.
That's a 2 though. I want to start with 1. Okay. 1. So we solve f of x plus h first. 4 divided by x plus h squared, and that's going to be equal to 4 over, I definitely let me do my bottom part first. We'll have x squared plus 2xh plus h squared divided by 4. All right. Number 2, we have x is h minus f of x. So we'll have x squared plus 2xh plus h squared divided by 4 minus, in parentheses, 4 over x squared. All right, now when we evaluate this, there's a little trick for fractions. Let me show you real quick. I know that if I have, let's say, 4 over 5, somebody's drawn.
That was me.
Somebody's drawn 4 over 5 minus, I don't know, let's do 3 over 7.
It should
Right?
disappear. I erased it.
It's still there. That's fine. I'm just going to write over. I know that if I
Okay.
have these, right? And the two denominators have nothing in common between each other, right? Then I can very easily make these equivalent so that I can actually perform this operation between them by just multiplying this one by the denominator as a hidden one of the other one. And we do that the same on both sides, right? So that's all that and this will, this would work out. I'm not going to work all that out, but I wanted to show you that because what I'm going to do here is the same thing. I'm just going to do the math in my head. So this x squared plus 2xh plus h squared compared to this x squared, they don't have anything in common. You might think that they do because they both have this x squared, right? But we can't factor an x squared out of this one over here on the left without changing it into some crazy stuff. There's no way we can get an x squared by herself. So these two actually don't have anything in common despite that x squared. So I'm just going to say this. 4 times x squared over x squared times x squared plus 2xh plus h squared minus 4 times x squared plus 2xh plus h squared divided by this denominator, x squared times x squared plus 2xh plus h squared. Sweet. So then this will work out to 4x squared. I'm going to distribute this all in one go. We have negative 4 times x squared is minus 4x squared. Negative 4 times positive 2x squared is negative 8xh. Negative 4 times positive h squared is minus 4h squared. We're going to divide this entire thing by x squared plus 2xh plus h squared. These will cancel, and we are left with just negative 8xh minus 4h squared divided by x squared times x squared plus 2x h plus h squared. All right, and our third step is to take f of x plus h minus f of x and divide that by h. So this will be equal to negative 8xh minus h squared divided by x squared times x squared plus 2xh plus h squared times 1 over h, because dividing by something is the same thing as multiplying by 1 over that thing, right? And then I will cancel this, one copy of that h and that entire h. So this will be equal to negative 8x minus h divided by x squared times the quantity x squared plus 2xh plus h squared. And that's our final answer. And I don't do different colors. I just do one color. I'm sorry. If you need more colors, tell me and I'll put more colors next time. All right. Any questions on
Yay.
that? All that stuff makes sense? I'm going to assume that's a yes.
That was a lot.
That's okay. The funny part is I think I did that wrong in my notes, so it's a good thing
You did it on here.
yeah.
That's perfect.
Yeah, I did it way wrong on my notes. Look at that.
Oh. Denominator. Okay, cool. So that is the difference quotient, y'all. Lots and lots of algebra. Okay. Well, if everybody's good with that, let's get into the domain of functions. All right. Anybody need this page still up for a second? Okay, good.
I think I'm a mistake on it. It should be 4h at the bottom. Whoops.
What'd you do?
At the very bottom, it should be negative negative 8x minus 4h.
Oh, yeah, you left that off.
Yeah,
Very easy to make a mistake.
Just
See?
drop that whole 4.
And they were all believing it. They're like, yeah, we're good to go.
I'm like,
All
yeah,
right.
of course, obviously.
That's right. Perfect. Okay, there you go.
I forgot it in the whole bottom.
Did I fix it? Yeah.
Negative 8xh minus, it just says h squared. It should be a 4 in that very first part.
Oh, in the very first one.
Yeah.
Ha. There you go.
Heck yeah.
There you go. Magical 4s just appear. Perfect. Okay, cool. So let's get into the domain of functions. We're basically finding where a function exists, what intervals a function exists on. And in order to do that, it's important to know what type of function we are dealing with. So we'll start with number 1. F of x equals x squared plus 5x. Does anybody know what type of function this is? Other than a quadratic.
Polynomial.
Polynomial, good. This is a polynomial function. And in order to be a polynomial function, all of your exponents must be whole positive numbers or the set of positive integers. So again, to be a polynomial, your exponents must be whole numbers and they must be positive whole numbers. That's the definition of a polynomial. Okay. And if this is a polynomial function, then the domain of any polynomial function is always going to be the set of all real numbers, no matter what. So our domain of a polynomial function is going to be from negative infinity to infinity. And the way to see that is, well, if I were to graph this function, x squared plus 5x probably looks something like this. Maybe a little off, but close enough. So we see that these tails keep heading towards, they'll never stop. So the tails will go to infinity as x goes to negative infinity and as x goes to positive infinity. So this y value will head to infinity as x heads towards positive infinity. And this y value will head towards infinity as x heads towards negative infinity. And this, again, can be said for any polynomial function. I could even rewrite or write the polynomial function y equals x. Y equals x is the graph of a line. And once again, we see a tail going to infinity, and we see a tail going towards negative infinity. They will keep going infinitely towards negative infinity and positive infinity. Therefore, our domain is the set of all real numbers. Okay, and that goes for any polynomial. All right, 2. We have g of x equals 3 of x over x squared minus 4. So this is a polynomial over a polynomial, which we can call a rational function. So if you ever have a fraction as your function, then this is going to be known as a rational function. And the way you find the domain of a rational function is, well, we have to think about fractions. What number can never ever be in our denominator of a fraction?
0.
0. Good. So for a rational function, you take whatever's in the denominator and set it equal to 0. So whatever is in the denominator of a rational function, you will always set it equal to 0. And now all we have to do is solve for x. I'll just move that 4 over, square root both sides, and we get for our domain that x equals what two numbers?
Positive and negative 2.
Positive and negative 2. But my question to you is, can x actually equal these numbers?
No,
No. Why not?
because then your denominator would be, well, your denominator would be 0.
Very good. So x can't be equal to positive or negative 2 because our denominator will equal 0. Okay. So let's talk about interval notation for a second. So I want to put this into interval notation. So we're going to put this domain in interval notation. And I guess the best way to represent that is to make a number line. So here's my number line. Here's negative infinity, and here's positive infinity. And here's my two numbers we just found, negative 2 and positive 2. So we know that we can be any number we want except for negative 2 and positive 2. So if I want to start my interval notation of the domain, what number am I going to start at?
Negative infinity.
Negative infinity. I come up the number line and I have to stop at what number?
Negative 2.
Negative 2. And then I will union the next set of numbers I can use. And where do I begin at?
2.
Not 2, but where did we
Negative.
stop at?
Oh, negative 2.
Negative 2. And then I go up the number line again and I stop at
2.
2. And then one more union and I begin again at
2.
and head towards
Infinity.
infinity. This is the interval notation for your domain. These intervals tell you where the function exists at. Same
That
thing.
math for Marines, man. Math for Marines.
Math for Marines.
1 + 1 = rock.
Here you go.
That's for the Army. The Army's the ones who gave you the a rock or something in the MREs.
Ooh, MREs.
My favorite flavor of Crown is naked.
Okay. Yeah. So that's interval notation, and let's keep going. All right. Number 3. You have the square root of 4 minus 3x. So the type of function we have here is going to be called an even radical function or an even root function. Okay. And to find the domain of an even root function, well, we have to understand some things about even roots. And here we're given the square root. So I'll just run through some numbers really fast. Can you take the square root of a positive number? Yes. I saw a nod. Can you take the square root of 0? The square root of 0 is
0.
0. Good. Can you take the square root of a negative number?
Yes.
Technically, yes. And you'll get what types of number?
An I, so imaginary number.
Imaginary numbers. Good. Good. So what that means is to solve for the domain of an even radical, you take whatever's inside the house, and to avoid negative numbers, what type of inequality would you put?
Greater than or equal to 0.
Good. Greater than or equal to 0. Greater than, to avoid negative numbers. Equal to, because you can take the square root of 0. Okay. And now all we have to do is solve for x. So we can move, what do you want to move, the 3 or the 4?
3.
Move the 3
No.
over, okay.
So move the 4 over.
Move the 4 over? All right, whichever you guys want. I think I'll move the 4 over just to see who remembers what happens. You get negative 3x greater than or equal to 0, not 0, negative 4. And then you divide by negative 3. And what happens when you multiply or divide by a negative?
You get a positive.
And flip the inequality.
You flip the
Right.
inequality. There you go. So you get x less than or equal to 4/3. So remember, on an inequality, whenever you multiply or divide by negative, the inequality will always flip. All right. Now let's put this into interval notation. All right. What this interval is telling us, or what this inequality is telling us, is that we have to be less than or equal to 4/3. So what number do you think I start at?
Negative infinity.
Good. Negative infinity. You come up the number line, and where do we stop? 4/3. But there's going to be a different type of notation here, right? Does 4/3 get a parentheses or a bracket?
Gets a bracket.
Gets a bracket. Good. So remember that brackets mean that the number is included or inclusive, right? All right. Cool. All right. Any questions on that one? All right. And then last one for this page. We have p of x equals 2 over the square root of x minus 1. And again, just to know what we're dealing with, this is going to be rational with an even radical. So I'll just say rational with radical. Okay. And all we have to do here to solve for this domain is take whatever's in the denominator inside the radical. And this time, can I set it greater than or equal to, or just greater than 0?
Greater.
Just greater than 0, because the reason we don't set it equal to is we can't have what number down there?
0.
0. And all you have to do here is solve for x. So you'll get x is greater than 1. Okay. Which means put that into interval notation. And if we have to be bigger than 1, what number am I starting at?
1.
1, and headed towards where?
Infinity.
Infinity. There you go. And those are domain. All right. Any questions on that? All right.
You're not going to show them set builder notation?
Set builder? I don't think it asks for it, but we got short set hand, right?
Yeah.
Yeah,
Let's
why
not
not?
get crazy.
Why not?
I just learned
Let's-
brackets.
Let's go over set notation. It's super fancy, guys. So we start with a fancy brace, right? And we say, for all x values such that x is greater than 1. Close fancy brace. So again, the way
How
to
would you
say
do that
this,
for the union one? The
Oh.
one from the rational function.
Oh, good. We'll get there in a second. So let me just say how to pronounce it. For all values of x, such that x is greater than 1. So that little vertical bar means such that. Okay. Ooh la la. So for this one, if you wanted set notation, we would just say for all values of x such that x can equal -2, x can't equal +2. That's it.
And my math lab will accept that, or do we have to use a union?
It's going to say, I think the majority of your questions are just interval notation.
Yeah, it'll specify. The messed up part is sometimes it'll tell you you have to put your answer in interval notation, but it'll ask you, the way it'll ask you questions, it'll be written in set notation. So you kind of need to get used to seeing both.
Yeah. So, and it'll already have most of it set up for you. It'll have like this, and then it'll have x equals some box, and that's it. So most of it will be set up for you already. So yeah, there you go. Good. Set notation. So fancy.
Oh yeah.
Okay. All right, last one, guys. Operations on functions. We are going to take these two fractions and add them, subtract them, multiply them, and divide them. As you see there, the sum, difference, product, and quotient. So let's go ahead and just practice these operations down below. We want to find the sum, difference, product, and quotient functions and determine the domain in each case. So before I even start with those operations, let's look at each of these functions and find out what their domain is. So for function f, what is my domain here? X cannot equal what number?
-2.
-2. And then for function g, what is my domain here? X cannot equal
1.
1. All right. So if we have these domains first, it's going to make our process a lot easier. So let's go ahead and try this out. So first we want the sum of both of these functions, which means all we're going to do is add these two functions. 1 over x plus 2 plus x over x minus 1. And we know that to add these two functions together, we need to have the same what?
Denominator.
Denominator. Good. So this fraction gets multiplied by x plus 2 over x plus 2. And this fraction gets multiplied by x minus 1 over x minus 1. Okay. Fair enough. What we're left with is x minus 1 plus x times x plus 2 all over the same denominator of x minus 1 times x plus 2. Okay. Now just clean up. And we get x minus 1 plus x squared plus 2x over x minus 1 times x plus 2. On our final cleanup, combine like terms, you should get x squared plus 3x minus 1 over x minus 1 times x plus 2. So that is the sum of both of these functions together. Now, all we want to answer is, what is the domain of our new function? And if you put together the domains we found above, we have x can equal what two numbers?
-2 or 1.
-2 or 1. Everybody good with that? And I guess you could ask yourself if you could keep going, if you could keep simplifying, but can you factor the numerator? Are there any factors of 1 that can make 3?
No.
No. Thank goodness, right? Which means we move on. All right. So that was the sum. And now we just get to the difference. Same exact thing. 1 over x plus 2 minus x over x minus 1. And once again, in order to subtract the fractions, we just need a common denominator. Multiply by x plus 2 over x plus 2. And then x minus 1 over x minus 1. And we get x minus 1 minus x times x plus 2 over x minus 1 times x plus 2. Distribute that x, clean up. X minus 1 minus x squared minus 2x over x minus 1 times x plus 2. Clean it up one more time, and we get negative x squared minus x minus 1 over x minus 1 times x plus 2. There we go. All right. And then, once again, nothing has changed. So the domain is -2, and x can equal 1. Okay. Not bad. Any questions on that page? All right. Last page. Product. So product, just multiply the two together. So 1 over x plus 2 times x over x minus 1. And this one's pretty straightforward because remember, when you multiply fractions, you do not need a common denominator. You just multiply straight across. And we get x over x plus 2 times x minus 1. Now that was nice. And our domain stays the same. X can equal -2 and x can equal 1. Okay.
So does that mean
Last one.
the
Go ahead.
domain stay the same across some difference, product, quotient?
Not the quotient. Only
Okay, awesome.
some product difference. Yeah.
All right.
Yeah. So now we do the quotient. So we take 1 over x plus 2 and divide x over x minus 1. And we know with fraction over a fraction, we will multiply by the
By the inverse, right? So flip it.
Reciprocal.
reciprocal. There we go. Reciprocal. X minus 1 over x. And then we multiply straight across. And we get x minus 1 over x times x plus 2. All right. So what's going to happen is our domain's just going to change just a little bit. There's going to be a new addition. So for my domain, we still have x can equal -2, x can equal 1, but we have one more addition. This guy right there.
The 0.
X can't equal 0.
All right. Let's write that.
Sorry, I have a question. Why
Go
can't x equal 1?
Yeah, that's my question.
Why can't x equals 1? Because it just originates from the original function. So if you left it as this and plugged in 1, we would still get an undefined answer. So no matter if we reciprocated and reduced, we still have to follow by the original domains.
So you can think about it like this. If we go back to where we started before we did all the work to put them together, and you started with just 1 over x plus 2 times x over x minus 1, and you plugged in values right there at that point, which you can totally do. You'll get the same numbers if you plug in x's at the beginning or if you work everything out and do it at the end. But if you do it at the beginning, you get an undefined value immediately. So that's why.
Does that work backwards also? Like, let's say we were working a product and we had what you have right now on the right-hand side. Right, so our f of x is 1 over x plus 2 and g of x is x minus 1 over x. Would that also say that we can't have it equal to 1?
Good.
Or
So
is it just because it started off as a quotient?
So if you're saying that the original was changing to x minus 1 over x,
Right.
and then you flipped them. Yeah. So then even with this, yeah. So here x can equal 0, but if you happen to flip it just like we did on the quotient, then yeah.
Right, but there it can equal 1, right? It would be
Exactly.
okay.
Exactly. Like right
So-
now you could equal 1. That's totally fine.
I guess that's where I'm kind of a little lost why we can't have it. I understand that in the original part, it's the quotient is x over x minus 1. But if we
Mhm.
do the reciprocal, right? So we don't
So you
have
have
1
now
on
x
the
minus
denominator.
1 over x, right? Right there.
Yeah.
So what we're still doing, because it's not finished, we're still solving, right? But like Carl and I said, since this new function originated from our original functions, we still have to follow the domain of our original functions.
Okay.
There's a small little, theorem that says no matter how you reduce, so if we started with f of x and reduced our function and got a new function g of x, this function would still have to abide by the original function's domain.
So for sure, the quotient is going to have the original domains. It may have an extra one.
Exactly. Exactly.
Okay, that clears it up for me. So always take from the original and from the end product.
Yeah. As long as there's a
Exactly.
rule, I'm okay.
Yes, there's always rules for all these. I guess another way to put it is, let's say that I had something such as x minus 4 over x minus 2. Like, I'm just talking more about this little theorem, right? So we know that for now, my domain is x can equal 2, right? If I factor this, I get x minus 2 times x plus 2 over x minus 2. And what's going to cancel here?
Your x minus 2.
Your x minus 2's. So we get a totally new function, x plus 2, which is a polynomial function. But remember, no matter how much you reduce, this polynomial function still has to abide by this domain, no matter what.
Mm.
So the original function then is what's most important.
Exactly.
Got
That's why whenever we get into rational functions after the first exam, whenever you start with a rational function, you should always find the domain first and then simplify. Always find domain and then simplify. Because imagine you didn't find domain on this first and you simplified. Well, guess what the domain of x plus 2 is? It's a polynomial. So you would assume that the domain is all real numbers, which is definitely incorrect to assume. So whenever you're messing with rationals, always find the domain first.
Got it.
And another thing, like I said, graphs always help. If I were to graph this function at
Show 'em on
2,
Desmos.
oh yeah, I can show them on Desmos. At 2, you would have an open circle on the graph.
Oh.
Yes,
Yeah,
but I guess we can explore that more.
You won't see the open circle on Desmos, but if you go over it,
It'll say undefined.
Undefined, yeah.
All right, so let's just go over what I was talking about. Go back. X squared minus 4 over, I had x minus 2, right? Yeah, I think so. X minus 2. So now, how's my graph going to look? Oh, my coordinates are way off. What if we just did, 10 to 10? Negative 10 to 10, and then I can just say negative 10 to 10, sure. That was weird. Okay, cool. So here's the function we're dealing with. But again, if we graph it, you're going to get an undefined value at 2. So if I drag my pen down until I get to 2, wherever you're going to be, come on. Maybe I need to zoom in more. There we go. There you go. Undefined, guys.
Undefined. Yep.
Because the function can exist at 2. There you go. Yep. Okay. So hopefully that helps out. Understand more. Okay. Other than that, that is the end of these notes. So if you have any questions, please stick around. We have 12 minutes. If you are good to go, then Carl and I will see you on Wednesday.
Learning has occurred.